Hey everyone, it's Judy. Welcome back to the OnTrack podcast. If you design in RF, microwave, or millimeter wave frequencies, today's podcast is for you. Today we talk to John Coonrad, who's the Technical Marketing Manager for Rogers Corporation, who's a global manufacturer of advanced circuit materials. John talks about what dielectric constant, or decay, and the various test methods for decay, and why data sheets can sometimes be confusing, and how all of this impacts your design. I think you're really going to enjoy today, so lean in and enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Hi, John. It's good to see you, my friend. Thank you so much for joining us today on the podcast. I'm excited to share you with our audience today.
Thanks for having me here.
Yeah, my pleasure. So why don't you start out by sharing a brief introduction about your professional background and a little bit about Rogers and what Rogers does.
Right. Yeah, so I've been in the industry, the printed circuit board industry, about 32 years, and that started back in '87 when Rogers had a division called FID, Flexible Interconnect Division. So I kind of tell people I was born and raised on flex circuits. And then over time, I kind of evolved into other things, did a lot of different engineering things for flex circuits. And then over time, I started working more with the Rogers high-frequency rigid board materials in regards to circuit fabrication assistance and technical support, things like that. And then the last about 11 years or so, I've been working with specifically RF characterization of our materials. And I do a lot of, RF testing on our materials, and then materials that we have in development, and sometimes competitive materials if I can get my hands on it, just to see, kind of get a finger on the pulse, so to speak, and see what's out there. I also do a lot of things in regards to marketing that would be like writing articles in trade magazines and present at trade shows and things like that. Aside from that, also, I'm very involved with IPC. So IPC has a committee that's D24C, and I'm the chair of that committee. Oh. And that committee defines high-frequency test methods for the industry. And right now we're working on defining test methods for testing materials for dielectric constant at millimeter wave frequencies. And that's quite a chore, but we're making pretty good progress, I think.
I didn't actually know that about you, about the IPC committee, but it makes perfect sense, and that's a good thing that you're the one chairing it. So just for some background for our listeners, sure. I had left the industry for a while, came back in 2009, I think, and I'd been focused on rigid boards, but when I jumped back in, I jumped into RF and microwave, which was like hopping on another planet.
Yeah, it's different.
It is so different. And so John was really one of the people that I learned a ton from. So we met sort of in those early days when I returned to the industry. So he's really been a mentor. So, I've squinted my eyes and sat through some of his talk and gleaned as much as I could, learned some new technical terms. And so I'm sure if you haven't had the chance to read some of his articles, I highly recommend them. So, like I said, I'm excited to share you.
Good.
For those who may not be acquainted with your work. So, along the topic of test methods, let's talk about dielectric constant, or decay, today.
Yeah, sure.
It seems like you have shared in the past, some of the things that you've shared with me, is that on data sheets, the decay can be inconsistent from data sheet to data sheet.
Right.
And I didn't even know, I always thought it's a hard science, it can only be one way, and that was really an eye-opener to me. So can you talk about actually what decay is? Let's start with a working definition.
Yeah, sure. Actually, there's a lot of definitions for decay, so I guess I'll start with the basic one, and that is decay is really the property of a material to sustain an electric charge by an electric field being applied to it. Basically, it's kind of a battery if you want to look at it that way. Like a battery would be very high in capacitance, high dielectric constant. So once you put a charge on it, it holds that charge. So dielectric constant is the ability to hold a charge and also to affect the electrical properties in regards to capacitance, I suppose. And there's a lot of different ways to define it, to be honest, but that's kind of a nice, simple way of defining it. But for test methods, there's a lot of different ways to test it, and I bring that up because the issue sometimes in comparing one data sheet to another is that the data sheets are not using the same test methods sometimes. So sometimes if the material has the exact same property with two different data sheets from two different vendors or something like that, you could actually have different values and it's still the same material. It's because of how they're testing it. So there's a lot of tricks to the data sheet, and of course none of that's really done with any negative intent. It's just that what happens is each company has their own industries that they go after, and because of that they realize that there's certain properties and certain test methods that will be that describes their materials a little bit more appropriate for the industry they're serving.
Of course.
So that's what it comes down to. So you do see differences in data sheets for dielectric constant, test method, and the values themselves. And it can get a little confusing. I'm not too sure how you want to go into this because we've done a lot of different things with process decay, design decay, and stuff like that.
So I think that's a great place to jump off because one thing Rogers does that is unique, and again, things that I've read or heard you talk about, is there being a difference between design decay and process decay. So why don't you talk about why Rogers chooses to do that? And I think it's really helpful, actually. So.
Yeah. Yeah, it's a little bit of, I have to give you a little history. This is a little bit of a long story, so I apologize.
It's okay. No, go for it. We want to hear your stories.
So what happened was many years ago, if you looked at our data sheets, you'd find one dielectric constant value on the data sheet. And that was true for decades. And what happened was, just for instance, if you look at one of our materials, that's the RO3010 materials, it's a high dielectric constant material. And for the test method that's mostly used in the industry for test and laminate, it has a dielectric constant of about 10.2. And what happened was, over time, we had customers come to us and say, we're using this material, we designed it, and how the circuit behaves suggests it's not 10.2 dielectric constant. It's actually higher, about 11.2. And we went down the path of investigating that in a lot of different ways. And it turns out the test method that's used to look at the raw material test, as we do, so we test the raw material, we don't test circuits, not for QA anyway.
Right.
But anyway, as we do the raw material test, it's a clamp strip line test. So basically it's a clamping fixture. You put the materials in, you clamp it together, and then you test it. And just the natural artifact of that test method is you do have some entrapped error, and error is a low dielectric constant. So with that type of setup, you're going to have a lower dielectric constant than a circuit that has no entrapped error.
I see.
And there's other things too. So that test method is a little sensitive to anisotropy as well. But long story made short, we found that what we really need to do is have a test method for us internally that looked at the process control and good QA type of test of the raw material, which is what we call the process decay. And then we defined another test method that is really looking at how the dielectric constant of the material is perceived in circuit form. So we'll go off and test microstrip transmission line circuits and extract the behavior of the RF performance to get the dielectric constant of the material in circuit form. And that's what we would call design decay. And that value is actually more appropriate for design, simulation, and modeling. So that's kind of the story on those two terms.
Okay. Well, I think that's helpful because I remember you talking about this somewhere and I was like, wait, what?
Yeah.
So it does give a more realistic real-world number, which I think is helpful. Right. But sometimes they still do want the other number, right?
Right.
So,
yeah, sometimes if you look at data sheets and you look at the test method, the clamp strip line test method for testing raw materials is a very common test method for what we do at Rogers and also what other laminate suppliers do. So that's usually a good thing to look at when comparing one data sheet to another data sheet. If they're using that same clamp strip line test, then more than likely the results are pretty good to compare one data sheet to another. If you are comparing one data sheet to another and there's different test methods, then the dielectric constant dissipation factor may be different because different test methods will basically exercise the materials in a different way, and you can actually get different results when testing the same material, actually.
So you mentioned clamp strip line. What other kind of test methods are out there?
There are a bunch. IPC has 13 different test methods to determine dielectric constant.
Wow. I
And
had
they all
no
have,
idea.
yeah, they have all kinds of different pros and cons to each test method. Has a series of good things and bad things. But what's most commonly used for materials is the clamp strip line test, which is, as the name implies, it's a clamping fixture. You put material inside the fixture, clamp it together, and it becomes the configuration of ground signal ground, like a strip line. And then you excite the resonator, look at the resonant frequency, and you get the DK and DF. Another test method that is pretty common is the FSR, the full sheet resonance test. That's also an IPC test method. And that method's kind of interesting because it's not destructive. So we can basically test a copper-clad panel and associate a dielectric constant number with that panel exactly, and then send the panel off. And what our customers do sometimes with that is they will do a correlation study between our FSR dielectric constant numbers and the end product and how it performs. And once they have that figured out, what they'll do a lot of times, they'll go to the fabricator and say, we need to have 3 or 4 different sets of tooling. So when the dielectric constant's in this range, use tooling A. If it's in this range, tooling B. So basically what they're doing is fine-tuning their product, so the end product is going to be optimum based on our FSR measurement.
I see. Which is more real world, really, for their specific design.
Right. Yeah, the only drawback to FSR is you're really testing a large panel, and you're setting up a resonance on a large panel, and large panel or large resonance means low frequency. So it's just the nature of it. It's going to be tested around 100 megahertz or so, and that's where the correlation study becomes really important. So if they do have an application that's running at 10 gigahertz and we're testing it at 100 megahertz, they need to understand the difference, and they need to do a good correlation to figure out what that is.
For those, go ahead. No, finish.
Well, I was going to say there's some other test methods as well. There's split post dielectric resonator, SPDR, and that's a real simple test method where you have a fixture that is 2 dielectric resonators top and bottom. You measure it empty as a reference. You put materials in, measure it again. How much the center frequency shift tells you about dielectric constant. How much the bandwidth changes tells you about dissipation factor. And then there's also waveguide tests, and there's quite a variety of tests out there for doing a lot of different things.
Well, I think what I wanted to insert here, because our audience here consists of many EEs that are designing their own boards. And one thing that I wanted to mention here relative to what you're sharing with us today is I've learned from people like Eric Bogatin and Rick Hartley that the material plays such a massive, because the way that electrical fields move through the dielectric, we tend to think, if we come straight out of university, that it's all about the traces, but the laminate has such a massive impact because really we're moving in an electrical field. And so I just wanted to insert that here for those who may have not been exposed to that, and which is what makes the work that John's doing so critical here. Especially in these high-frequency designs, which, by the way, what are those applications? Pretty much everything these days, anything that's wireless. Think IoT, automotive. What else, John? Cell towers.
Oh, yeah, just about everything. But what I've been working with a lot lately is more millimeter wave. And as the chip industry has advanced the technology, now there's more and more applications popping up for millimeter wave. And millimeter wave, just for a band of frequencies, is anywhere from about 30 gigahertz on up. And microwave frequencies is about 300 megahertz to 30 gigahertz. And what I found was, over time, just from doing a lot of testing and looking at a lot of different applications, as you get higher and higher frequency, of course, the wavelength gets smaller, and that means the wave itself gets more sensitive to any differences of the material. So where at 2 gigahertz, if you see a difference in dielectric constant of 0.001, that may not be that big of a deal, but at millimeter wave frequencies where the wavelength's really small and it's very sensitive to differences, that kind of decay difference could be a very big deal. And some of the things we've been looking at is the 77 gigahertz radars in automotive cars, and they are sensitive to dielectric constant differences in consistency. And of course, if you get that wrong, then the car may not do what you want it to do. So it's a pretty big deal.
Well, let's talk about that. If you don't, let's talk about the implications. So if the decay is off, what are some of the potential impacts and implications? You just mentioned one, automotive. If that's off, you could crash your car.
Yeah.
So what other things can you share with us relative to the hazards of your DK being off?
Right. Yeah, it depends obviously a lot on the application. And to be honest with you, most of these applications are pretty smart. That they're designed so if something unusual happens, nothing real bad happens. But there still are, big concerns. Like if you have circuits used as guidance systems for the military, then obviously you don't want to get that wrong. That could cause for someone having a really bad day. And then there's things like the base station equipment. That's a different scenario, but what happens there is if the dielectric constant drifts or changes because of temperature, which is actually something a lot of engineers may not be aware of, but dielectric constant will change with a change in temperature.
Oh.
And if that happens in a base station when it's hot and cool outside, then the performance changes, and then the noise floor changes, and then you drop calls more, or something like that.
Okay.
So it depends on the application, but DK being consistent and how DK behaves over frequency or over temperature is actually a really good thing for the designer to understand.
Okay, that makes a lot of sense. So what would you say, you talked about some of the more common test methods. What would you say from the perspective of a designer, sort of misunderstanding, the relevance of DK? What are the, I guess, the pervasive misunderstandings and how that impacts a design engineer today?
I've seen several things that are a common error, and it's not any fault of the engineer usually. It's just that in academia they don't teach a lot of the things related to DK changing with frequency, DK changing with temperatures, and sometimes they're just unaware of it. And the biggest example that comes up a lot is something we call TCDK, which is thermal coefficient of dielectric constant. And what happens is engineer will develop a new circuit, new application in the lab, fine-tune it, everyone's happy, send it off to the field, and then it goes through wide swings in temperatures in the environment, and the DK starts changing with these different temperatures, and they didn't account for that, and that's a really big deal. We've seen that I don't know how many times in a year, and maybe even more than once a month, that I run into issues where TCDK is not being accounted for well. So that's something that is normally not found in in academia, but it is a real-world issue that has to be dealt with.
So how do designers and engineers learn about that?
Right. There's some information out there. IEEE is a fantastic website. I go to that a lot, and there is some information there. But that's typically information that is at the materials level. So the people making the materials, we understand the properties of the materials very well. And we're usually the people that understand those quirky things about DK change with temperature. And the other thing is DK will change with frequency. And for a application that's a very narrow band, or it's just operating in a small range of frequencies, then you're not going to see a big difference. But there are applications where they're trying to do very wide band and they're trying to have performance over a wide range of frequencies. Then the DK changing over frequency can be a real issue. So normally that information is best found at the people that formulate the materials, such as us. And there are some other papers out there as well, but they're usually not, I wouldn't say quite as practical. They're more theoretical, which is fine. Just understanding the topic is a good thing.
Right. Is there anything else out there? So you're obviously running into this one a lot. Are there other ones that you're seeing that are sort of pervasive?
Yeah, I guess the thing that I run into a lot is when a dielectric constant is, well, let me back up a second. For test methods, there's two different ways to really evaluate the dielectric constant in a very general sense. So you can evaluate the dielectric constant in the material level, as we do with our clamp strip lining test, or on circuit level, as we do with the microstrip transmission line testing we do for design DK. But there's a lot of customers doing also ring resonators and different kinds of circuits, and based on that, they extract the dielectric constant. And sometimes there's circuit influences that are not accounted for, like plated finish, ENIG, plated finish, electrous nickel immersion gold. Most people realize that actually causes more losses, but a lot of engineers don't realize that affects the phase, and it can actually make a difference from And I've done studies where I test one circuit that's built off the exact same material, same design with bare copper, and another circuit with ENIG. And the circuit with ENIG will definitely have a shift in how it reports dielectric constant. So it's not that the dielectric constant of the material changed, it's that the ring resonator behaves different for capacitance, which means the circuit is perceiving a different dielectric constant, if that makes sense.
That, like, how do you get your head around that? Like, again, I always, when I'm here, I try to stand in the shoes, you know, of the people that are designing circuit boards out there, and I'm like, that would be something that I would imagine would easily escape my attention.
Yeah, everyone. I agree.
So you mentioned IEEE. I know you guys have some great resources, but like, again, how do we, as a designer, so you mentioned obviously places like Rogers or IEEE, like how do we, and I know you write about it, so again, how do we just avoid these pitfalls?
Yeah, just learning more about the topic in general is about the only way to deal with it. But I put together a file for one of our materials that was used a lot in 77 gigahertz automotive that looks at a huge amount of variation that needs to be considered. And it's variation when you do how the circuit perceives the material overall. You can see big variations in how the circuit influences the extraction and the decay, I guess. So what I'm saying is there's things like copper surface roughness. It does vary from one batch to another, and that makes a difference on how the circuit perceives decay. Plate and finish, I already talked about some. There's also normal fabrication issues where when you make a circuit, especially at millimeter wave, where it's really sensitive to differences, when the conductor sidewalls in a cross-section is rectangular versus trapezoidal, that makes a difference too. And then how thick the copper is or how thin it is, that makes a difference for some coupling features. And there's quite a list of things that the designer really needs to deal with if they want to capture all these different variables. So it's not a trivial thing to do. Again,
it's not. And like I said, just for me personally, coming back into the industry and then jumping in this end of the pool, you know, luckily I had people like you and Dale Doyle that on speed dial, you know, or reading your stuff or attending your seminars. But I was overwhelmed from the perspective of being a board fabricator. I basically, you know, was blogging about this at one time on the Microwave Journal website about the fabrication side of it. And what I came to understand is how many ways as a fabricator I could actually screw up a designer's board, you know, by the way we processed it. And I'm like, for so many years, board manufacturers, for example, were so used to thinking about more mechanical, like tolerances and things like that. We weren't thinking about surface finishes or the way we etched could. We could, in other words, we could be inside IPC standards and still screw up your performance of your board. And that was crazy to me, like, you know. And so this, anyways, it's an intriguing topic, and there's so much to learn about it. So, what else would you recommend? Oh, one thing I wanted to ask you, John. You mentioned that you're seeing a lot more applications in the millimeter range. What's driving that?
I really think that what actually started the whole drive with more millimeter wave applications, I think, is really the chips. The manufacturer and the design of chips are now able to do much higher frequency applications. In the past, it was difficult for some of these chips to be able to have good, stable performance beyond 30 gigahertz. And now they have chips that are easily at 77 gigahertz, some at 94, some even beyond that. So I think the chip industry and the functionality that they offer to a circuit, that kind of enabled everyone else. And once that was understood, then the printed circuit board designers, they started applying these chips to different designs like radar or backhaul at 60 gigahertz or these different things. And I think that's kind of what started the whole thing, was actually the chip manufacturers. But yeah, we've seen a lot of applications at a millimeter wave now. Mostly, I guess by the bulk would be the 77 gigahertz for automotive and 60 gigahertz backhaul, but there is a lot of other applications out there as well.
You know, one thing that, you know, from my limited sort of technical depth on the subject, but one thing became apparent to me is it seemed like it was really because of the speeds are going to where they are, it seems like we're starting to kind of hit our heads on the limits of printed circuit board manufacturing. Do you see that?
Yeah, that's a really good point, because as you get the higher and higher frequency, like these 77 gigahertz radars, they have features that are pretty small, and these features have to be pretty well defined. In the radiating elements of these 77 gigahertz radars, they have what I would call a stepped impedance pattern, where you have a narrow conductor, wide conductor, narrow conductor in series, and that narrow conductor is around 4 mils usually, and most fabricators can deal with that. But the problem is when you transition from a 4 mil wide conductor to a 100 mil wide conductor, you want it to be a very abrupt change by design, but that's not the way the fabricator will do it usually. It's just the nature of how you etch a circuit.
Yeah.
And that little difference actually does make a difference. At 77 gigahertz, big difference. At 10 gigahertz, probably not a big difference. But little etching anomalies that you may not even consider at lower frequency really become a big deal when you're at that higher frequency and the wavelength is so small that it can pick up these differences.
Yeah, that's the kind of thing I'm seeing, because really on sort of a, microscopic level, those little anomalies and changes can make a huge change to that performance. And so one thing that I was looking into myself, I sat on the board of eSurface for a while, is like, do you see additive manufacturing coming to play there, or what are some things that from where you're sitting you see as sort of enabling technologies perhaps coming down the pike?
Right. Well, for circuit fabrication, LDI has been around a while, laser direct imaging, and that's definitely a plus. At these millimeter wave frequencies, the geometry has to be very well defined, and LDI is a big plus, and I know there's more fabricators using that, so that's a good thing.
Yeah.
But some of the additive things, like eSurface, and I think there's a few others out there as well.
Veritech, we've had a Veritech on the show, and I think they're doing some good work. So
Right. Yeah, so those are really interesting, because at millimeter wave frequencies, what I found in some of the studies I've done is if the copper is very thick, or you might think of it as the conductor standing up off the substrate higher, you have more fields fringing in the air, and you can have more problems with what's called surface waves, or these waves kind of interfere with the wave that you do want. So when the copper is taller and more fringing and other things, it actually changes the performance of the circuit. So if you could have a thinner copper, not only does that help the circuit fabrication, because thinner copper usually means they can define the geometry a little better or more. Yeah. And then also thinner copper means that you should have less problems with these surface waves, and these surface waves are kind of it's a long strange story, but the copper thickness does seem to matter. And then if you have circuit features that are coupled, like have two conductors side by side and they have electric fields coupled, the difference in the copper height of thick and thin does make a difference in how they perform. Again, at microwave frequency is not a big deal. At 77 gigahertz could be a really big deal.
Yeah, it's interesting days to me. I always keep my eyes on people like a Veritech, or, additive manufacturing seems like a potential solution, but I'm always keeping my eyes out, and so I'm always curious to see what you're seeing.
Yeah, I think it's interesting.
Yeah, it's something we're going to have to solve over time,
Yep.
I don't see us slowing down.
No, I don't either. Yeah, I've talked to several designers that's doing automotive with some unusual type of automotive applications, and some at 94, and some are talking up around 140 gigahertz.
Oh my gosh.
And I'm not sure how to deal with that in a lot of different perspectives for connectors and cables and things that you would connect to it, but there's definitely interest there apparently.
Well, and then it makes me wonder if the kind of line between chip design and board design are going to blur, like if we're going to have to adopt that kind of precision, and that miniaturization is going to go to like chip level design. So it's interesting day. So
indeed.
Well, this has been fascinating, and if you're willing, I'd love to have you back and just talk about the materials.
Sure.
Just composition and all of that, because I think that's a fascinating thing to learn.
Absolutely.
And interesting to talk about reinforced, non-reinforced, pluses, minuses. That's a whole storm that I think that people would enjoy learning. But this, just test methods and decay, is a fascinating topic. So I thank you for sharing it. So I want to share everything you can throw at me, John Coonrad. So I know you have a wonderful tech hub. So can you give us some ideas of things you can share so people can learn more?
Sure. Actually, I took the easy way out and I wrote it on the back of the board back there. So that's our tech support hub address. And
I can't
really,
read it though.
Oh, rats. Well, it's www.rogerscorp.com/techhub.
Okay, well, I'm going to share it in the show notes because I can't read your whiteboard.
Oh,
so
sorry. Anyway,
okay.
At the Tech Support Hub, we have a lot of different resources there. We have white papers, and we have also articles that we wrote in different trade magazines. We have papers that we present at trade shows. We have videos. Some of the videos are several different Rogers people presenting at trade shows. Some videos are more short, simple kind of tutorial. And some of those videos are what I do called Coonrad's Corner. And they're usually 5 to 7 minutes long, and they're really just a quick introduction to an RF topic. And that's one thing I'd like to bring up here for what we've been talking about. I have 2 Coonrad Corner videos on, I think it's called What RF Designers Need to Know About DK Part 1 and Part 2.
Okay.
And that's probably the best thing to look at, to be honest, because it has a lot of what we talked about today and more details as well.
Well, I am a proud member of the Tech Hub, and if I need to know anything, it is like the one-stop shop. So
Good.
I would highly recommend. It's free. You can go on. Yep. There's tools. Do you guys still have your app too? You had an app with a calculator on it, I think. Is that still active?
Yeah, we got multiple calculators on the website. Some of them are just basic, and it does come back to what I was talking about earlier, the TCDK. So you can put in there the dielectric constant at room temperature, and then the change of temperature, and it's going to tell you how much that material will change dielectric constant with the change of temperature. And then we have the Mwi Calculator, which is an impedance and loss calculator, and that's been pretty popular, and that's on our website too. And we have several other software tools as well.
Well, I just think you guys are the bee's knees because
Cool.
I have learned so much from you personally and also from the Tech Hub, and it was like a go-to. You've done a wonderful job of informing designers who are in the weeds in this territory as you know, frequencies go up and up. So we really appreciate you, and I will definitely share all of that. And Coonrad's Corner is my fave because even I can understand Coonrad's Corner. And they are, you know, small bite-sized pieces of really good, powerful learning. So John, I know IMS, which is the International Microwave Symposium, is your probably biggest show of the year, which I think is going to be in Boston this June.
Right.
So we'll also share that.
Okay.
Are you going to be out and about? I know sometimes you're out speaking or at events.
Right.
Do you have anything coming up on your calendar shortly?
Yeah, and IMS in Boston, I think that's the first week of June, if I remember right.
Okay.
Anyway, I'll be presenting 2 micro apps there, and the micro apps are usually, they're kind of informal technical papers, and they're open to anybody, so you don't need a special badge. And one of them is on glass weave effect, and I did a study last year on that, and I kind of give a quick summary of it. And the other one is on plated finishes. Had to stop and think about that. But basically looking at the differences between a bare copper circuit and circuits with ENIG and immersion tin and silver and different things like that and what should be expected. So that's 2 things I'll be talking about at IMS MTTS in Boston.
Perfect. And for anyone who wants to go to that show, I went for many years. It's a fantastic show, like drinking from the fire hose. And those micro apps are done right on the show floor, like in an open theater style. So it's easy to jump in and out of them. So I can't recommend that show enough. So if you want to learn more, and then Rogers always has a massive booth there.
Yeah,
John and other smarty pants people like him are in the booth. And so I highly recommend that. Well, John, thank you so much for your time. I know there is no grass grown under your feet. You're a very busy guy, so we really appreciate your time.
My pleasure.
Hopefully we can do this again, and we'll talk more about, you know, the composites, right? What is in your material and how that affects performance, and that maybe another time when I can squeeze you away from your busy schedule.
No problem.
Okay, thanks so much.
Right.
To our listeners, thanks so much for joining myself and John Coonrad from Rogers Corporation today. We look forward to hanging out with you next time. Until then, remember to always stay on track.